Where we left off in the last few sessions was building up the idea of stochastic gradient descent and the optimizers used for stochastic gradient descent. And so as we enter this section on optimizers, it really involves the specific parameters for calling stochastic gradient descent and ways that you accelerate the convergence to the optimal minimum. And so the first idea that we use is momentum. It's merely momentum. And so if you look at how this entire concept gets encapsulated in the code, it's merely one more parameter following the learning rate to say momentum equals 0.9 or something lower, which would be lower like 0.2 or so on. We're going to talk and see in a minute exactly what that difference is and why you really want to choose something like 0.9, which Giron refers to in the book as it'll speed up your training by 10 times. So this particular section, referring to the book on page 351 for momentum, what happens with momentum is simply that you are updating your gradient, just as you do with learning rates. You're updating the gradient by looking at the local gradient before. So he introduces, or in general, we introduce a vector, a momentum vector called m here, multiplied this momentum value, and that's the 0.9 or so on. But this momentum vector m is really what takes those previous values of the gradients. The whole idea is how fast is it moving towards a particular minimum, and then use that and subtract that from your gradient. This may not seem exactly quite intuitive, but if you bear with me for just a moment, I want to show you something from yet a different chapter. And this I got from attending our fellow Salim, a fellow student here, Salim, who taught very well a section on gradient descent and optimizers and so on yesterday at another study group. And the book that they use is a different one, but without going into all those details. In that book, I think they do a slightly better job of being able to explain that same idea. What's different in here is where Giron uses the momentum vector m, this book refers to it as v, but it's still, and the momentum factor, beta, is still there. And so what happens is that let's start with a simple equation that's laid out like this. This equation has its local minimum at the origin, 0.00. And so we're trying to get to 0.00. And if we use a very basic stochastic gradient descent, you can see that it oscillates wildly while trying to get to 0,0 in this picture over here. And so if you begin to use, oh, I'm sorry, wrong picture, this one. It oscillates wildly as it tries to get to its local minimum. But if you use momentum, you do a much better, faster job of being able to get to this point here, the origin point, to the minimum. And that's because of this clever little trick of looking at previous gradients and using that as a way to update each new gradient, similar to how you use the learning rate.
One quick question.
Yes, sir.
M vector, does it get initialized or does it get learned?
As I understand it, it follows history. It tracks, it's just retaining the history of what the previous gradient weights were. And so it isn't necessarily learning, but it's just simply looking back at its own history, its own logs, and to say, okay, what was the gradient in the past session?
It's okay. I'm like it. We are subtracting the gradient of function from m times beta. So
no, so go ahead. Sorry.
So I'm just trying to understand that then m get reduced by the gradient on
M
every
gets
step.
Yes. So M takes, so one of the things we do is the next one takes the average, but it takes the past gradients and then it weights the past gradients by this value beta, this momentum value of 0.9. So you're taking, if the last gradient value was a certain amount, then portion of that is what you retain, and then you use that to update your new value of what would be the next new group, the input for what the gradient will get.
And thetas are the weights.
Are the weights.
The weights. So we are adding the momentum to a weights
to the
rather
weights,
than subtracting the gradients. So wouldn't it like the weights get bigger and bigger?
Well, as I understood it, the weights, I had that same thought that shouldn't it be a subtraction rather than so, and I noticed in this other different book, and I don't want to compete one book against another, they do the subtraction.
Yep.
So I did have that question, and honestly, I sort of resolved it for myself as, well, the change must be negative. So the value of M should over here in this from equation number 1 in equation 11-4, this one will be a negative, hence you add it to the gradient, but that'll have the effect of this being a negative vector.
Right.
I think if you notice, the first line is also different. That's what I was confused as well. I think it might just be notation difference.
Yeah.
And I've read a blog and it uses notations on the right from diving to deep learning rather than the notations from left, which doesn't make very much intuitive sense. But please, someone, if someone knows better, please jump in on the notation.
Yeah. So as Mesh, you said rightly that M is obviously a negative number on the left on a Giron's book, and that M vector has a huge value initially, and then it starts decaying slowly and slowly, so that our weights down below in a second step, we have the weights first get updated with the bigger margin, and then as we go down the valley, the M start getting, the negative of M start getting smaller and smaller.
Smaller and smaller, correct. Which allows us to converge a lot better, as opposed to if we did not use that momentum method, then we'd be oscillating wildly as we're approaching the minimum. And so we're just trying to...
The weights don't seem to have anything to do with larger or smaller, right? The graph you're looking at is the loss function. The loss is becoming smaller. That is irrespective of whether your weights are big or small. Does that make sense?
Say that one more time, please.
The figure on the right that you're looking at is the loss function.
It's the loss function.
So the loss is becoming smaller, that's right. But that has no effect directly with, you can't correlate and say that for your loss to become smaller, your weight has to become smaller.
Smaller.
Your weight can be big or small.
That's right.
It just needs to hit the right weight so that your loss becomes small.
Yep.
Yeah, but then weights, if you look on the left, the weights get updated with the momentum.
Right.
So that's the point I was trying to make, that ultimately the momentum is contributing to the weights.
It is, correct.
So
it's not decaying as you go down.
Well,
momentum,
that's
momentum, intuitively, if you think of what it is basically like, let's say you have two instances, right, where momentum it plays a role is that, let's say you're going in the direction down the slope and you're hitting towards the minimum and the loss function. So what momentum is basically trying to say is that if you're going in the correct direction, it's saying use 0.99 of my last value and use just 0.1 of my current updated value. So what happens is that you're mainly using your previous accumulated values to move in this direction. Now, let's say there's an instance where you suddenly have like a valley, or let's say you suddenly are going to jump. Now, if you jump, you're going to oscillate. So what momentum is saving you from oscillation is by saying that use 0.99 of my previous, which is the stuff that you trust more, right? That's why you're weighing it by 0.99. Yeah. And you're using 0.1 of the current one, and that is the one which we said jumped. So it's going to not jump because you're using only 10% of that, and you're believing more on the previous value.
That makes sense.
So going big or small is kind of not, I don't think that directly makes sense here, because your M can be positive or negative.
Right.
That can either make your thetas go up or down. I mean, like, you can't really say that you started with a big theta and you're starting to go smaller, you're going to go up, right? Because theta can be anything. Thetas can be positive, negatives. They can be larger than 1, less than 1. Anything is possible there. So it's just updating your theta, which can be a plus or minus over there.
Correct. Yeah. So yeah, exactly. I'm like, the momentum is updating a theta rather than other way around.
Yes, for sure.
Yeah. Right. Yeah. Right. Got it.
And Raquel, do you know how does momentum vector get calculated?
You mean like initially how it is set?
Where the value comes from.
Yeah.
I don't know how you actually initialize momentum. I'm not very sure how that happens.
My understanding was it's just supposed to look at history.
Right, but
so it's averages.
If I may, I guess that it's initialized to 0, and in fact, in the beginning, it's equivalent to just a regular stochastic gradient descent. If momentum at the first step, it's equivalent to stochastic gradient descent. Momentum is just equal to learning rate multiplied by negative gradient.
I see.
That's the value when you set beta, the momentum parameter equal to 0. That negates this entire term. And so that resolves
we initialize M vector to zeros, all zeros. The resulting momentum at the first step will be negative learning rate by gradient. You see?
Yeah.
Okay.
Okay. Yeah. And the other question I have is the notation on the left seems to they don't go in line with the notation on the right, because if you look at it, notation on the right is actually if you look at if you feed the first line into second line, that would be xt equals to xt minus 1 minus the learning rate times the beta vt minus 1 and minus gt t minus 1. Whereas on the left, you know, the sign is a little it's different. They don't equal each other. Can someone explain that?
I think it's the two things which I got from this conversation. I'll try to explain. It slightly makes sense to me on the left. So as Raquel was saying, momentum is the gradient, the current gradient plus portion of the last one. Okay. And as Arto said, for the first part on a first cycle or on initially when M is initialized to 0, then the first M is going to be nothing but just the gradient, the initial gradient, which is a minus of n theta delta of a theta. Yeah, that one. So that's your first gradient. And then obviously this will get added or subtracted to the weights on the step second. And when we come back to this, now for the second step, we have again the gradient, and then gradient of that particular cycle plus the last portion, which is 0.9 of a last one. And obviously both were negative numbers. So it is the negative goes into M. And then in the second step, now what we are doing, instead of subtracting only the portion of the gradient, we are subtracting the current gradient plus 0.9 of the previous one. That's what I gathered.
Yeah. And if you look at on the right, it's minus previous gradient and minus the current gradient. So that's where I get a little confused, because they're actually different.
I would say don't look at the right, because we haven't had a chance to read the text that goes before it. We don't know what V is, we don't know what X is, we don't know what G is. So I think that if we had a chance to read that, we would understand it. But I think we should pay attention to Jeroen's book, because that's the one that we have access to, and the one that we're reading, and the one that we've read for this lesson.
Yeah, my apologies for confusing everyone with introducing these equations. My intent to use this book on the right was really to show these plots where you can begin to see the effect of going from this oscillating effect of trying to reach the minimum to when you use the momentum, it performs a lot better. And then, of course, if you reduce that value of the momentum parameter beta to something much lower than 0.9 to say 0.25, just as Jeroen also explains over here. He says stick to 0.9 because it's going to speed up your momentum optimization, your training 10 times faster than normal gradient descent. Well, sure enough, here's kind of why. If you use the lower value of beta, it'll still begin to oscillate. It'll get to the minimum, probably take longer. That's it. So moving on a little bit, if we're done with that portion, the next trick is using what's called the Nestorov accelerated gradient. Comes from a paper in 1983, et cetera, and where what we're doing for this one is slight different variation. It looks the learning rate portion of the gradient, it will look one jump ahead as well. So the difference being in regular momentum, where we use the learning rate and so on, factor to the value of the last gradient, this one will jump ahead and use the next gradient value in order to get a different version of that momentum vector and then subtract or add to that momentum vector to the gradient. This one's a slightly trickier, even in my head, going to an earlier question we just had in the session. How do you compute this? How do you even get this value? To me, seems much trickier to code it out, but of course,
yeah, and
it's just that.
I'm like the portion which you have highlighted, that's the gradient of a function plus the momentum gradient
effect.
Yeah, yeah. So I'm like, what does it mean? So we are, I'm not sure. So it's not only the gradient of a function we're looking at the gradient of the momentum with respect to the weights.
That's actually an estimate of a gradient of a function at the one step ahead. That's not exactly that gradient, because we end up with not exactly the same update, but it's an estimate. it will be closer to a gradient at the next step, but not exactly it.
Mm-hmm. Okay, I'll take it.
If you look at the expression 11-4, and if you look at the second part where it says theta gets theta plus m,
Mm-hmm.
but then if you substitute in for m from equation 1, you see that theta gets theta plus beta m minus the minus the normal weight update. So it's theta plus beta m is the key here. Theta is getting an update that consists of theta plus beta m plus the normal update. So that's what they're doing in Nestorov. They're saying, let's, instead of evaluating the loss function at theta, evaluate it at theta plus beta m, which is, as was pointed out, is really the next step, is really where it's going. I don't know if that made any sense. Does that make sense?
Yeah, like what you're saying, it makes sense, but it's intuitively the term which we have been using, the overall gradient, like the delta of theta j and in brackets theta. But now we have this added terms. So I'll just take it that this is like as the estimation of the gradients for the step ahead.
Right. And so we just have to go with exactly that point, that take it as this is faster, generally faster than regular momentum optimization.
Yeah, thanks.
And I wish I had tested this out with some data sets and so on to be able to show you all exactly why and how and where it would break. But
yeah,
which
I will do. Which I will do later in Excel. Sorry to interject.
Oh, perfect.
I'll do that with Jeremy's Excel book. Yeah, sorry.
That's it. That takes us through Nestorov, accelerated gradient descent. Oh yes, and there is one, before I forget, there is this one interesting diagram that points to how much faster that would be. So where this white zone is your minimum, measured by the shading based on cost, you can see that Nestorov, at least he puts it, will take us closer that way, as opposed to a regular momentum, which might still cause some further oscillations in this instance.
See, so when you look at that picture, the blue dotted line is essentially the same as the solid line displaced over to there. And so if you, in other words, if you evaluate the gradient at the blue point, the blue circle to the left, where it says starting point, if you evaluate the gradient there, you would get that blue vector, solid vector, right? And so that's what so now he's saying that's what would happen if you add that update. That's the same as the dotted blue line. That's just displaced over there. And so you can see how that takes you in the wrong direction. Whereas if instead you evaluate the gradient at the tip of the black arrow, that's the step ahead thing, right?
The step ahead, because the momentum moves you here.
Right. If you evaluate the gradient there, then it's pointing it's pointing more towards the minimum because it's now closer to the minimum. It knows where the minimum is better than when you evaluated it back at the blue dot.
So apply the learning rate, you end up over here. And if you apply the learning rate after the momentum, the blue dot comes here. And then with
takes you in the wrong direction, right?
Right, but still closer. This point is further away than this point to the right of the blue dot. Right?
I'm not sure what you said.
The starting point, and then apply the learning rate. There is no dot here.
That's right.
But this is still closer to the minimum than this other blue dot.
Yeah.
Is this so? You know, the blue first dot, is this the first gradient? So I'm like, why we have new delta 1 twice, the dotted blue line and the solid blue line? What it's trying to say?
Okay, the solid dot on the left, okay,
Yeah.
that's if you apply the gradient, if you calculate the gradient there, then that solid blue arrow is the direction of the update. Okay.
Yeah.
But if you instead apply the gradient, if you instead jump ahead first by beta m and apply the gradient at the point indicated by the tip of the black arrow, calculate the gradient there, and that gives you, and then you add it there, that gives you the green arrow, which takes you directly towards the minimum. If you didn't do the look ahead thing, you would apply the same as the solid blue arrow there, which takes you, which is the dotted blue arrow. That's the same. That's basically the same as the solid blue arrow displaced over there to where the tip of the black arrow is. So if you didn't do the Nestorov update, you would get to where that dotted blue arrow takes you. But if you do the Nestorov update, then you get towards where the green arrow takes you, which is the right direction.
Okay, so okay, I get it what you're saying. So we are saying Nestorov is fix the direction of your gradient as well as the magnitude as well, because the green arrow is that's the green dot is our optimal minima. That's where we want to be, but now the magnitude from the black to, or like the magnitude of overall, if you look from solid blue all the way to green dot, so the magnitude coming from all the way from the solid blue to green dot is less than as we have been on the blue dot on the right side. The top.
I guess, okay, so here's the way to understand it. If you look at the sequence going from the blue dot on the left, adding beta m to the black arrow, and then adding the update, adding the eta times the gradient there, that's where momentum takes you, to the blue dot on the right.
Yeah.
If you just apply the momentum formula. But if you apply the Nestorov formula, then you advance by beta m, then you calculate the gradient. So you would first advance to the tip of the black arrow, that's adding the beta m. Then you take the gradient at that point and add it. Okay. And that gets you to the green dot. So it's the two different ways. The blue dot on the right is where you would get with the regular momentum update, but the green dot is where you'd get with the Nestorov update. Does that make sense?
It makes sense. Yeah, absolutely. Yeah, thanks.
I'm curious, before we continue, has anyone implemented this momentum and Nestorov updates in real world with any kind of data set, whether that be image processing or anything else? All right, just curious. Wencheng, do you want to take it over?
Yeah. Let me take it over.
And thank you for everyone's patience and just hearing me struggle to explain this. This is still a relatively new concept for me at this level.
You did very good job. Thanks for your time, Mesh.
Thank you.
Okay, so the reason why I was a little confused is I also on the notations I've seen like Sebastian Ruder, someone who's I believe it's the same Sebastian Ruder, but he also used the same notation as it's in the in this book, Dive into Deep Learning book. So that's why I was a little confused. And And I feel like it's also more intuitive to always have this kind of minus sign as he does it here, rather than, you know, always the plus sign. So yeah, so I think it's just more intuitive to make it consistent. Then he, you know, he kind of switched back to like minus sign here, minus here, and then back to plus sign. So yeah, anyway, so okay, so we're gonna talk about RMS prop. Sorry, autograds. Autograds. Okay, so let's read it a little bit quickly. As the coding is just, you know, as Mash showed, it's just one single line, so we don't have to go through the coding. So let's just read through the text. Gradient descent starts by quickly going down the steepest slope, which does not point straight towards the global optimum. Then it very slowly goes down to the bottom of the valley. It'll be nice if the algorithm could correct its direction earlier to point a bit more towards the global optimum. The autograd algorithm achieves this correction by scaling down the gradient vector along the steepest dimensions. And obviously, the mathematic equation is quite intuitive. You're just using a square of the gradients and plus s. Then you square root of that. So you kind of square root it back plus the epsilon. And this is a division sign, element-wise division sign. So you kind of use your current gradient to you scale your current gradient down by the square root of the current gradient plus epsilon. So and plus the previous one. So that's that. And so let's read about it. The first step accumulates the square of the gradients into the vector S. So recall that this symbol represents the element-wise multiplication. This vectorized form is equivalent to computing Si equals to Si plus derivative of J theta divided by derivative of theta I square and square of that for each element Si of the vector S. In other words, each Si accumulates the square of the partial derivative of the cost function with regard to parameter theta I. If the cost function is steep along the ith dimension, then Si will get larger and larger at each iteration. The second step is almost identical to gradient descent, but with one big difference. The gradient vector is scaled down by a factor of square root of S plus epsilon. The symbol represents the element-wise division, and epsilon is a smoothing term to avoid division by 0. Typically set to 10 to the power of -10. This vectorized form is equivalent to simultaneously computing this. Now I didn't get how this is transformed from this. If someone knows, that would be great, and please feel free to jump in. How he kind of transformed this into this. For all parameters theta I, in short, this algorithm decays the learning rate, but it does so faster for steep dimensions than for dimensions with gentler slopes. This is called an adaptive learning rate. It helps point the resulting updates more directly towards the global optimum. One additional benefit is that it requires much less tuning of the learning rate hyperparameter. So that here's a comparison between gradient descent and autograds. And as the text says, it points more towards the direction of the global minimum, as it's shown here. The former can correct its direction earlier to point to the optimum, right here. Autograt frequently performs well for simple quadratic problems, but it often stops too early when training neural networks. The learning rate gets scaled down to so much that the algorithm ends up stopping entirely before reaching the global optimum. So even though Keras has an autograt optimizer, you should not use it to train deep neural networks. It may be efficient for simpler tasks such as linear regression though. Still, understanding autograt is helpful to grasp the other adaptive learning rate optimizers. So that's autograt. And I thought this is relatively straightforward calculation. I just didn't understand how this was transformed. Anyone else has questions or comments?
What was the question with the equation, Vanchang?
I just how was this formulated? How did this come from this?
So equation 2 is nothing but theta is getting updated with theta minus learning rate times whatever your gradient is. So you're just substituting the gradient in, right? Where gradient is nothing but delta of the loss function with respect to, derivative of the loss function with respect to the weights.
Mm-hmm.
So that dou j of theta by dou of each weight is nothing but the nabla of loss, right? Which is that inverted triangle j of theta. And then you're dividing by the square root of s plus, which is nothing but the square of those gradients that is still there in the equation. The equation 2 basically shows you like in the vector slash matrix form, whereas the theta I1 is just showing it to you as like each element, what is happening, right? Each weight, what is going to happen for each parameter. Does
Okay.
that make sense? Like,
yeah, I probably need a little bit derivation on this to fully understand. But thank you for that.
Okay, so there's no derivation you need to do, but I think that if you look at the equations 1 and 2, they're a little bit confusing because of this new notation with the crosses and the slashes. I think the best way to do it is to ignore those equations and look at the one in italics where he does it element by element, the one that Rekil was just pointing to. That's the one that you use when you implement it. And what? Yeah, and.
Okay.
Yeah, and it's just basically the same as equation 2, but applied element by element.
Okay.
Yeah, and so the thing to look at in that equation is the denominator, the square root of s. It says that directions that have a history of a large gradient, they are the update is reduced in those directions. That's the S. The S tells you the history. It measures the history of how big the gradient has been in the past. And so a direction I that has had large gradients in the past, that update will be squelched a little bit because it's divided by the square root of S with respect to the other directions. Pardon?
Where does the division of this come from?
Oh, well, if you look at the equation 2, okay, it says take theta, subtract the normal update, which is eta times the gradient, divided by that square root of s plus epsilon term. That's the same thing. If you block out the last part for a moment, if you block out the square root of si plus epsilon term, just block it out with your thumb, and then you'll see that that's what the normal update looks like, right? But it says, instead of making that normal update, divide it by the square root of si plus epsilon. That's all it's doing there.
Okay.
Does that make sense to you? I mean, maybe if he would have used parentheses to block off the normal update, then it would be easier to look at maybe.
Okay.
Wenchang, were you asking about the division sign that you see? That's not actually division, that's just the derivative. So it's do.
Oh, that's not division sign.
That's
Oh,
right.
got
That's
it.
derivative.
Oh,
Yeah.
Okay. That makes total
It's the
sense then.
derivative of j of theta with respect to theta I.
Oh, okay. That makes total sense. I wish you could have just printed this better.
Right. So if you
Or just
actually
enclose it in parentheses before you divide by the square root of s.
Oh,
anyway.
that makes total sense now. Okay.
So then if you pull out that last square root of si plus epsilon,
Yeah.
and put that under epsilon, I mean eta, that is basically what your adaptive learning rate is.
Yes. Okay. That makes total sense now. Okay. It was just a confusion over this print. Okay. Makes total sense. Great. And anyone else wants to make a comment on this? And it seems like this can't even be used for deep neural networks. It's more for quadratic problems or linear regression. I don't know when this was invented. Okay, so if no one has any questions or comments, let's move forward to RMS Prop. As we've seen, grads runs the risk of slowing down a bit too fast and never converging to the global optimum. The RMS Prop algorithm fixes this by accumulating only the gradients from the most recent iterations, as opposed to all the gradients since the beginning of training. It does so by using exponential decay in the first step. The decay beta is typically set to 0.9. So it's basically beta times your previous s plus 1 minus beta, which is 0.1, times this, again, square of your gradients, your current gradient. And you use that to fit it into a square, to again kind of scale your current gradient with the square root of the s. So so if you compare the second step, it's actually the same, but the first step is somewhat different. It's first step, for AdaGrad, it uses s plus the square of the gradient, whereas here it uses kind of the exponential decaying factor of beta and or rate of beta, and it's set to 0.9, and so 0.9 times s plus 0.1 times the square of the gradients. So it's altered by adding a exponential decaying rate of beta of 0.9, and that's how it's kind of coded with Keras. And don't worry, if you're getting kind of confused on all kinds of optimizers, we will go through one exercise of comparing all of these and how they behave differently with a simple linear regression. And this is developed by Jeremy Howard, and I added in a couple graphs. So just hang in there if you get a little lost, and hopefully it will get a little clearer after we go through this exercise. And it seems like we do have time for that. Okay, so back to this.
So on the RMS prop, you're basically kind of applying momentum to the squared gradients.
Yes, exactly.
Yeah.
Exactly. Intuitively, that's what's different between RMS prop and momentum.
RMS prop and AdaGrad.
Say that again?
RMS prop and AdaGrad, that's what the difference is. You add in momentum to AdaGrad, which makes it kind of to the square of the gradient.
Yes.
Which makes it RMS prop.
Yeah, exactly. Yeah. Okay, and the row arguments. corresponds to beta in equation 11-7, except on very simple problems. This optimizer almost always performs much better than AdaGrad. In fact, it was the preferred optimization algorithm of many researchers until atom optimization came around. So if you think about it, like this is actually also kind of adds on top of momentum with the square root and sorry, the square and the square root. And we'll see that in Excel, how Jeremy Howard implemented. And so, and also I believe this was developed by Geoffrey Hinton, if I remember correctly. 16, yes. So this algorithm was developed by Geoffrey Hinton in 2012. And amusingly, this since the author did not write a paper to describe the algorithm, researchers often cite slide 29 in lecture 6 in their papers. So I think Jeremy also mentioned this fact that this actually did not come from a paper. He just kind of put it in his Coursera course in the slides, and that's that's RMS Prop. So that's an interesting fact. Okay, let's back to the text. Okay, yeah, go ahead. Yeah.
Could you go to figure 11.7?
11.7, yes, right here. Oh, figure 11.7 or equation 11.7? Figure 11.7, yeah.
Okay, so my question is, like, I understand that AdaGrad decays the learning rate in a faster way for if the square of the gradient is larger, but how are we sure that you reach the minimum faster than gradient descent? Because AdaGrad would decay the learning rate for both theta2 and for theta1, right? So are we reaching faster because we choose a much higher learning rate for AdaGrad initially compared to gradient descent? Is that the main intuition?
No, I think the main intuition is to look at that drawing, and you see that there are two directions. There's one direction which is a steep direction. That's the vertical direction. The gradient changes steeply, whereas in the horizontal direction, the gradient changes much more slowly. So you can imagine the AdaGrad updates for the vertical direction for theta2 are going to be attenuated by the factor in the denominator, by the square root of s, because it has a large gradient. And so instead of paying attention to the
theta1 gets attenuated as well, right?
Yes, but not as much. And so that's why the purple path, which is what you would do without AdaGrad, becomes the yellow path, which is what happens when you attenuate theta2 updates more. It's
but
not allowing.
Does it necessarily mean that you would reach the minimum faster?
It means that you would reach the minimum more directly. See, the yellow path is a straighter line.
But the main point is that we have to reach fast in lesser number of steps, right?
Yes, and so if you look at
the actual direction does not matter, right? We have to reach
well, no. If you look at the length of the purple line, that's longer than the length of the yellow line, and so that means that the yellow line can get there with fewer updates because its arc length is shorter. It's in some sense it's a shorter path, and so you can get there with fewer updates.
Okay, but yeah, I would, it's not completely intuitive, but
I agree. It's not entirely intuitive, but
I guess since AdaGrad kind of attenuates your learning rate, you can start with a much higher learning rate as opposed to if you were starting with gradient descent.
That's a good point. Yeah.
Does anyone know how does the learning rate gets updated here? Because it's not shown in the equation.
Actually, you divide the gradient descent. You divide the gradients by the root of s plus epsilon, right? That's equivalent to. I think that's equivalent to kind of modifying, reducing your learning rate. That's what he means by.
So this is not changed.
No, that's not changing.
Okay, got it.
Since you're dividing it by the root of s plus e, it's equivalent to the same thing.
So just
I
this.
think what Rekil said is really nice. He said that you can think of it, you can think of AdaGrad as equivalent to using an adaptive learning rate, where you replace the learning rate eta with eta sub I, which is equal to eta divided by the square root of si plus epsilon.
Okay, that makes.
That's a nice way to think
sense.
of it. That Rekil said.
Thank you, Rekil. Thank you, Joseph. Yeah, that makes more intuitive sense.
If I may add a bit, look, if you imagine, may you scroll a bit lower?
Yeah.
If you imagine like starting it in the leftmost point, you may end up oscillating in y-axis, you know, because
Yes.
and this adaptive learning rate will decrease this in oscillating axis.
Yes.
And
we
will go directly to the minimum in this case. You know, that's where it's really helpful, this technique.
Are you talking about diverging and going beyond the local minima?
No, like oscillating, we will go to the minimum, but like rolling to like up and down, down.
Like in the drawing that it's like in the drawing that that Moss showed us, you know, where it oscillates up and down like that if it overshoots.
Okay, so it's over. You're talking about the case when it overshoots the local minima and diverges, right?
No, it overshoots, like instead of going on the purple path, it goes a little deeper and then it has to come back and then up and down. It has to go on a sort of an oscillating path to get to the minimum. In the case here is a mild case. The case they showed with that purple path, that's kind of a mild case. But what if it kept going and then it would have to oscillate back and forth in order to get to the white area?
Yeah. So you're saying since the learning rate drops, that won't happen, right?
Well, that's what Arto was pointing out, is that because it's attenuating the learning rate in that steep direction, it's not going to allow it to oscillate so easily. It's going to go on a straighter path.
Yeah, that makes sense. Yeah.
Okay. All right. Anyone else? Okay, Adam. Adam, which stands for adaptive momentum estimation, and I believe this came out 2014. It combines the idea of momentum optimization, RMS Prop. Just like momentum optimization, it keeps track of exponentially decaying average of the past gradients. And just like RMS Prop, it keeps track of an exponentially decaying average of the past square gradients. Okay, and if you look at this kind of the momentum, and this is the RMS Prop, and you kind of scale that with a factor, and then you update your weights with a combination of the momentum and RMS Prop. So that's what Adam is. And in this equation, T represents the iteration number. So let's go through each line of this a little bit more detail. So again, this beta 1 is the hyperparameter that you set. It's usually 0.9. So 0.9 times your previous momentum vector and minus 1 minus 0.9, that's 0.1 of your current gradient. And this is your S, which is your previous S times, it's usually 0.999 for beta 2, and now it's plus 0.001 times the square of your current gradients. And then you feed this into this equation and divide by 1 minus 0.9 to the power of your current iteration. I don't know, because Jeremy Howard actually didn't implement these two steps, so I don't know. And I think Jaron did explain why these two steps exist, and this is similar to this one. It's just using beta 2, and then you use theta plus eta times your m hats, element-wise division by square root of s hat plus epsilon. So even though it looks a little complex, but it's just a combination of momentum plus Rms Prop. So if you just look at step 1, 2, and 5, step 1, 2, and 5, you will notice Adam's close similarity to both momentum optimization and Rms Prop. The only difference is that step 1 computes an exponentially decaying average rather than an exponentially decaying sum. So if you compare this to the momentum right here, so this is, I think that's what he referred to as exponential decaying sum. And this is the exponential decaying average. And these are actually equivalent except for a constant factor. The decaying average is just 1 minus beta 1 times the decaying sum. So, so that's that. And step 3 and 4 are somewhat of a technical detail since M and S are initialized as 0. They will be biased towards 0 at the beginning of training. So these two steps will help boost M and S at the beginning of training. So these are just technical details of implementation. And
that's the debiasing term that Jeremy Howard refers to, if I'm not wrong. Otherwise, basically, if you're doing exponentially weighted averages, the terms that are there that you see initially, that is what he talks about at 0, is pretty much seen every time you make this computation, right? Even when you're calculating something at step 100, you still have the factor of something at 0, which is contributing. The biasing kind of helps to nullify that effect as you go forward. Like,
yeah,
see much more recent than something that happened hundreds of years ago. Intuitively, that's how.
Yeah. Now I understand, Rakil, I understand this is just your past gradients, right? Your past iterations gradients, if it's batch 1. What about, let's say we have a mini batch. How is that calculated, your previous M and S?
Why should that be any different from a batch? Like, why are you differentiating between a mini batch and what did you say, a normal batch?
Stochastic.
Ah, okay, like that. Okay.
Is that just average or something else?
It should be just the average though, still, right?
Okay. Okay.
That's what I think. I'm not sure, but yeah, that's what I would think.
Okay. Okay. Got it. Okay, let's keep reading. The momentum decay hyperparameter beta 1 is typically initialized to 0.9, while the scaling decay hyperparameter beta 2 is often initialized to 0.999. As earlier smoothing term epsilon is usually initialized to a tiny number such as 10 to the power of -7. These are the default values for the atom class. To be precise, epsilon defaults to none, which tells Keras to use Keras.backend.epsilon, which defaults to 10 to the power of -7. You can change it using Keras.backend.set epsilon. Here's how to set it. Create a atom optimizer using Keras right here. And since atom is an adaptive learning rate algorithm, just like AdaGrad and Rms Prop, requires less tuning of the learning rate hyperparameter Ada. You can often use the default value Ada equals to 0.001, making atom even easier to use than gradient descent. If you're starting to feel overwhelmed by all these different techniques and we're wondering how to choose the right ones for your task, don't worry, some practical guidelines are provided at the end of this chapter. So we'll go through that next time. And he also mentioned there are two variants of atom, and also the computation complexity of that. So we'll go through that right now. Atom max, I mean, he didn't explain this in great detail, so I'm just going to read through it. And I'm sure, you know, one would probably need to read a paper to understand more about this. Okay, so notice that in step 2 of equation 11-8, step 2, which is right here, atom accumulates the squares of the gradients in S with a greater weights for more recent gradients. In step 5, if we ignore epsilon in steps 3 and 5, which are technical details anyway, atom scales down the parameter updates by the square root of S. In short, atom scales down the parameter updates by the L2 norm of the time decayed gradients. Recall that the L2 norm is the square root of the sum of squares. Atom max introduced in the same parameter as atom replaces L2 norm with the L infinity norm, a fancy way of saying the max. Specifically, it replaces step 2 in equation 11-8 with S equals to max of the beta 2 times S to the gradient of J of loss with respect to theta. It drops step 4 and 5 and it scales down the gradient updates by a factor of S, which is just the max of the time decayed gradients. In practice, this can make atom max more scalable than atom, but it really depends on the data set. In general, atom performs better, so this is just one more optimizer you can try if you experience problems with atom on some task. So that's the kind of equation, and I think he just explained a little bit, and we probably need to read the paper to understand more about how atom max works. And the other one is NATM. NATM optimization is atom optimization plus the Nestorov trick. So we'll often converge slightly faster than atom. In his report introducing this technique, the researcher Timothy Dozat compares many different optimizers on various tasks and finds that NATM generally outperforms atom, but is sometimes outperformed by Rms Prop.
2, 3, 4, 5, 6.
I think, Joseph, do you mind muting? Is that Joseph? I believe it's Joseph. Yeah. Thank you, Joseph. Okay. Adaptive optimization methods, including Rms Prop, atom, and NATM optimizers are often great, converging fast to a good solution. However, a 2017 paper by Ashia Wilson showed that they can lead to a solution that generalize poorly on some data sets. So when you're disappointed by your model's performance, try using plain Nestorov accelerated gradient instead. Your data set may just be allergic to adaptive gradients also check out the latest research because it's moving fast. Anyone knows what the state of art is on the optimizer? I'm curious to learn that.
I think Tiok123 posted a paper that was just last week, and it seems to compare all the modern methods, and so on. I haven't read the paper, but I think if anybody wanted an up-to-date review, that's a good place. The paper would put you off at first because you see it's 30 pages, but in fact, all of the relevant material is in the first 8 pages, so it's not going to be too hard to read.
Cool. Thank you, TYOC123. I believe that's the paper?
Yeah.
Okay. So, benchmark process. Budget, is that in dollar amount? Tuning, schedules, results. Okay, this is cool. Comparing all kinds of optimizers in the heat map. Okay. Seems very cool paper. So if you, it was already posted in Zoom chats. So if you're interested, feel free to read that. Okay. All the optimization techniques discussed so far only rely on the first order partial derivative, which is Jacobian. The optimization literature also contains amazing algorithms based on the second order partial derivatives, the Hessians, which are the partial derivatives of the Jacobians. Unfortunately, these algorithms are very hard to apply to deep neural networks because there are n square Hessians per output, where n is the number of parameters, as opposed to just n Jacobians per output. So, you know, I think for some of the data sets, like image data sets, n square will be pretty painful, considering, you know, each feature is just a pixel. So, and I don't know much about like Hessians and how that could be, and it seems like it's very useful as well. It's just the computation complexity is a bottleneck, and I don't know the kind of how that behaves with respect to the Jacobians, and how that can be helpful on updating the weights. If anyone knows, please feel free to jump in.
I believe that's just second order derivative, so like derivative of a derivative, which means we can estimate like a change in this gradient, not only a change of, like gradient is a change of parameters we want to get, but Hessian is like estimation of a change of a derivative, which will provide like useful information.
So like if you're trying to estimate a function, where the function's going to go, given where it is at this point, it's helpful to have this. And so far, the techniques we've looked at just consider the first derivative, but you can get a better estimate if you also take into account the second derivative, right? And people have studied, you know, if you've taken first year calculus, they may have introduced the Taylor expansion. You may remember that, which is basically an expansion of the update of a function, an estimate to a function that includes all the higher order derivatives. So the more higher order derivatives that you keep in the Taylor expansion, the more accurate a function approximation you'll get. So the techniques we're looking at keep the first order derivative. The techniques he's talking about keep the second order derivative as well, so give you a better estimate, but they take longer to compute. So I guess they haven't found a lot of widespread use in machine learning because of the large numbers of parameters that these models deal with.
Yeah. Absolutely, absolutely. Cool. So I'm gonna skip this section, and you can feel free to read that. But let's just
just a
yeah,
minute. Any idea
yeah.
why that gives n squared Hessians? Why isn't it 2n? Or are we taking product of parameters or something? But that won't be the right.
Yeah, anyone has any idea on calculating a derivative of derivative? Why that
Isn't it with
results?
each weight? So if you have n weights, so basically for each weight you would have to compute it with respect to n of them, right? So
Yeah.
when
So it's n for, I mean, n Jacobians.
correct.
And
So
when you take the, yeah, go on.
So then for n Jacobians, you have to compute with respect to each of the n Jacobians will be with respect to each of the other n Jacobians, right? The derivative of those. So n into n, that's where I assume that the n square comes in from.
Aren't we just taking second derivative with respect to the same parameter?
Right, so that's what I'm saying. But for each of them, you need to take with respect to each of the parameters, right?
But
Okay.
they are independent, right? Why would
Well,
you?
let's say you have a model that has two parameters, x and y, right? You have to take, for the Hessian, for the second order derivative, you have to take partial derivatives with respect to x squared, partial derivatives with respect to y squared, and partial derivatives with respect to x and y. So, you know, it's really n squared. There are four
That's
terms.
2n,
Even
right?
even though two of them, even though the thing is symmetric, so the derivative with respect to x and y, you know, the partial with respect to x and y is the same as the partial derivative with respect to y and x. So there's a little bit of symmetry that reduces it, but it really is on order of x of n squared. You can imagine that the Hessian derivative, the Hessian is a matrix. It's going to be symmetric around the diagonal. It's going to, you know, but it's still going to be on order n squared terms.
So we take the derivative of, suppose we have a loss function j, and we take dou j by dou x, and then we take derivative of that with respect to y as well.
Yes.
Okay.
And with respect to x again. And, you know, so you know, you can think of it as four terms, you know, the
But
derivative
why
with
would that depend on y? I mean, why would the derivative of loss with respect to x depend on y?
it wouldn't. It's just that when you take the Hessian, you have to take the derivative, the second derivative of the loss. So you have
That would be 0, right?
no. The second derivative of the loss could be the derivative with respect to x, and then again with respect to x. And then, or
Yeah,
the,
that wouldn't be 0, but derivative of the loss with respect to x with respect to y.
no, because the loss is a function of both x and y. So it does have a derivative with respect to x and with respect to y.
Okay, yeah. Okay, I'll go
Okay.
through this.
Yeah.
So for example, if the loss were a function like f of x equals x squared plus y squared, then you have a derivative with respect to x. You have a derivative with respect to x and y, right?
Okay. I think we have to keep going, and because we're running out of time. Okay. So we can talk more about that later on Slack. But thank you, both of you. SGD, SGD, momentum, Attagrat, Rms Prop, Atom, Natom, and Atom Max. Their convergence speed and convergence quality. So I believe the convergence quality is how fast, sorry, how, like perhaps it's the direction.
I think whether you see the local minima or not.
Yeah. That makes sense in terms of the definition of convergence quality. And convergence speed is obviously very self-explanatory, and they're all stored here. So you know, without it, you know, that doesn't need too much explanation. And obviously, the atom and atom variants seem to be performing the best, and including Rms Prop as well. So that's that. And okay, so without further delay, let's dive into this quick exercise. And I just want to show how Jeremy Howard implemented momentum, Rms Prop, and atom. And okay, so this exists in the hold on, let me see. Let me just give you guys.
Cheng, I'll share the link on our shared drive and Slack if you want to focus on the Excel.
Yeah, absolutely. Thank you so much, Mash. So yes, it's in the GitHub course v3 in one of the Excel files. Okay, so and we start with basically this data sets of linear regression, and the true values of the parameters is 2x plus 30, and then he kind of just randomly generated a bunch of data points with respect to x and y, and then this is just basically x times your 2 x times your 2 plus 30, and he just generated a bunch of x, and so randomly between 1 and 100, and use that to times x plus 30 to get your y. So just like I believe 30 data points ish, and we were trying to estimate this function 2x plus 30. So, and a is 2, b is 30. So keep that in mind. That's the parameters. Okay, so this is the kind of the basic gradient descent, and this is the momentum. This is Rms Prop. This atom annealing, and again, kind of using that annealing of the learning rate, scheduling the learning rate, which we'll learn, later on next section. So I won't touch upon this until next time. Okay, so gradient descent. This he kind of did it here. How you actually calculate the gradients of B and A, and this is the error. And we all know this, right? This is just basically your square. Can someone mute? Okay. And this is just basically ax plus b minus y and square of that. That's your error, right? That's your sum square of error, and total loss. And using that to kind of calculate the derivative with respect to your b and 8, and that's how you calculate it. And so, and these are your data points, okay? And this is the newly kind of, I believe this is the newly updated parameters, okay? And this is your prediction. So this is basically using x times your estimated parameter plus the slope, which is intercept, and that's your prediction. And this is the square, your actual target minus your prediction and square root of that, okay? And so that's kind of your prediction error. And this, I believe, is this is just kind of using another way of calculating the gradients, and just plus 0.01, and kind of calculating in that way. But we have a formula here, and so then he kind of just does the back propagation by hand, and which is 2 times E6 minus B6, which is this one, right? So that follows this formula of calculating the gradients. And this again uses this times your x, and that's basically what it is here. So dA is here, and dB is calculated using this. And that's how you calculate the backpropagate, the gradients used for backpropagation. And the gradient descent is, again, theta equals to theta minus learning rate times your gradient, right? So your new A is basically your D6, right? D6 minus your gradient of 8 times the learning rates. Okay, that's your new A. Okay, and your new B is calculated in the same way. Again, you know, your intercept, your estimated intercept minus the learning rate times the back probability, the gradient of B. And so let's reset this to like 1, 1. And the function is ax plus b again, and the true function is 2x plus 30. And he set a macro to run it 5 epochs per like click on the run, and you can get RMSE right here, which is basically here, right? So he kind of took it from here, and this is just the square root of this sum of this square, basically using your error, and square of them, and square root of that sum, and that's your RMSE, right? And with 5 epochs, and it drops from, your RMSE drops from 104.74 to 103.99, and he graphed it, right? And the way how I did it here is I just want to see how your new A gets updated and your new B gets updated, okay? And how your gradients, how your partial derivative of B and how the partial derivative of A is fluctuated. And notice how when we said gradient descent fluctuates a lot, and we really meant, you know, how these gradients can fluctuate quite a lot, and all the way up to like 6,000. And that's why gradient descent can converge very slowly because of that oscillation or fluctuation. And if you look at this, we know that this is 2x plus 30. So intercept, you know, after 5 epochs, still 1.27. The slope is 2.56. Let's hit another 5 epochs. Okay, slowly creeping up. But RMSE is dropping very slowly, okay? And this is why we're not using gradient descent. We're and people came up with momentum Rms Prop and atom, which helps the algorithm to converge faster. Okay, and we talked about what momentum is, and uses kind of a the way how Jeremy Howard implemented this is it uses an exponential decaying average factor of beta, and so it more correlates with let's go back to this, more correlates with this, okay, rather than this, okay? So kind of
that equation that you're showing, Wenchang, the way it's written is like that, but conventionally the 1 minus beta does exist on the second term. You're just seeing the beta here on equation 1, right?
yeah.
So second term does have the 1 minus beta, but apparently they don't write it. But conventionally that is sitting in there.
Yeah, yeah. So I agree, and that's why it's probably more helpful to look at this.
Yep.
Yeah. So, and that's what he did. Okay. We got 5 minutes left. Okay. So this is the momentum, and it was taken from here. And again, this is more like a batch rather than mini batch, but it's more like a batch momentum. And so this he didn't explain how these were calculated, but it's similar to and that's why I was asking the question how the momentum is calculated when we have a batch, but it could be an average. But notice how this was calculated. Okay, we're using the J4, which is this 0.9 times the in J1, which is sorry, J4 is this momentum times the J1 0.9. So momentum times 0.9, as we said, and your current gradient times 0.1. So that's your momentum. So you're not using your dB, your gradient to update it. You're using if you look at here, it's C6, right? C6 minus J6, which is this, times your learning rate. So using the momentum to update rather than your gradients, because and that's how it's updating, right? And the momentum is calculated with 0.9 times your momentum, your previous gradient, right? And your K1 times, which is your current gradient times 0.1. And that's how it's calculated.
Hey, Wencheng, if you want to go down to J34 and look at the formula in that cell, then you can figure out how that was calculated, because you mentioned you wanted to know how, oh, it doesn't show.
Yeah, it doesn't show
formula.
that. It doesn't show that. Yeah, yeah. So that's why I was a little confused. But let me just, yeah. So I just want to show like how this behaves. Okay, so it seems to be a little faster than gradient descent. Okay, and okay, so it goes up a little faster than gradient descent, and notice how the oscillation and fluctuation of the gradient is actually smaller than the gradient descent. Okay, and because of that exponential decaying average factor of 0.9 and 0.1. Okay, and let's go through RMS Prop really quickly. Again, we know RMS Prop gives you a square factor, and then you square root of it, right? So square factor of this and square root of that. Okay, so and that's exactly what we did here. You're doing the square of that. Okay, square of the current gradients, which is the green of this, square that, and times the 0.1. Okay, and use the 0.9 times the previous gradient. Okay, and you can see that here. And the way how you update it, again, you want to scale by the square root of that. Okay, and that's the square root implementation in Excel, and use C6 minus F6 times the learning rate and divided by square root of that. Yeah, square root of that. Okay, so and let's see how it behaves. quickly. So notice it jumps all the way up to 3.18 after 5 epochs. Okay. So it's already very fast, right? It's converging fast. We know the true value of B is 30, and A is just fluctuating, right? Okay. So very quickly, that's RMS prop. Again, it converges a lot faster than momentum. Adam. And we know it's a combination of momentum and RMS prop from the equation that we got it from here, right here, right? And again, he didn't implement these two technical steps in Excel, and it's probably because it's probably very simple linear regression, so he didn't do it. And the way how we do that is, again, square root of that, right? And in the end, you have a square root update of M and S, right? So that's your momentum, and that's your square root of your S, which is RMS prop. And we went through how momentum is calculated and RMS is calculated. So you have your beta 1, which is 0.9 here, beta 2, which is 0.9999 here, okay? And look at how fast it can converge. 5 epochs. And you can even use learning rate of 1. And it almost jumps to 15 already after 5 epochs. 22, 26, 28, 29, 29.5. So after like 25 epochs or so, we're almost close to the true value of the function. And yeah, so that's that. Okay, it's 3:02. Anyone else has a last comments or question?
I think with Adam, a thing to keep in mind is that you can use larger learning rates without things diverging. Yep. That is the other fact that kind of helps you like converge faster.
Mm-hmm. Exactly. Yeah, and we're using learning rate of 1 here instead of 0.0001 and 0.02, and we're just literally using 1 here, and it's not. Yeah.
That adaptive learning rate comes into play, right?
Yeah.
It can be something high, and when it can use it, use that, or else it will rescale itself so that it.
Yeah, absolutely. So this notebook is this Excel book is quite helpful, and I added some visualization charts and stuff. So hopefully
Can you jump momentum tab once again, sorry?
Yep.
And go to like J33.
J33.
Or anything on J. What is the calculation there he's doing? Because that should be the same for J34, right?
Not really.
What happens
but
if you reset
yeah,
the value set for J34?
But you're using basically the previous momentum times the 0.9 plus the current gradient of and times 0.1. But notice how he calculated these two numbers. I don't know how he did that, but then feeds back into this. And so the new epoch would use these two numbers, which came from here, and calculate that. So yeah, so that's that.
Interesting. Okay.
Yeah. I don't know how these two numbers got calculated, and it's not an average exact, because average is negative 16.88, and average of that is 3 point. Yeah, so I don't know how these two numbers were calculated. Yeah. Okay. Yeah, notice, the first line is actually using these two numbers. So yeah, all right. Anyone else has any questions before we close? This is pretty cool and pretty handy. Feel free to do these calculations yourself. I was just building a kind of practice for myself, and I did that hand calculation of back propagation, which is quite helpful because, you want to have a deeper understanding of how a simple linear regression is back propagated using Excel, which is quite helpful, visualization wise. So that's that.
Hey, Wenchang, do you know what Adam_ANN is?
Adam annealing.
Oh,
So scheduling.
oh, okay.
Yeah, yeah. So, and we will talk about this, this tab specifically in the next section when we talk about learning rate scheduling. So. Okay. All right. So on that note, I want to thank everyone for joining the session. Really appreciate it. And this Excel book is I mean, I had my own tweaks, but the original Excel book exists within the FastAI's GitHub. I think Mash probably already posted that. And so that's that. Okay. Well, and I want to